Standard analytic consensus treats prime numbers as a stochastic distribution. This behavior is often modeled using random matrix theory, a statistical framework used to predict the energy levels of complex quantum systems, where individual outcomes appear random but follow collective patterns. The number OS models primes as a deterministic binary state machine locked into a rigid grid. The foundational rule is that all prime numbers, excluding 2 and 3, are bound within a 6n plus or minus 1 arithmetic architecture. Under this framework, primes function as phase-shifting glitches that drive the geometric engine. Reframing prime behavior from a random variable into a measurable structural state provides a pathway for navigating the mathematical hardness of factorization. The system squares the base unit of 6, establishing a modulus 36 primary coordinate grid. Modulus 36 captures the second-order interferences occurring within the 6n plus or minus 1 prime framework. The number OS categorizes primes into distinct orientations. The T1 state, with left-handed polarity, encompasses all primes following the 6n-1 format. The T0 state, or right-handed polarity, encompasses all primes following the 6n plus 1 format. Categorizing primes by this arithmetic spin allows the system to predict phase shifts during complex recursive operations, turning static numbers into dynamic controls. These arithmetic parameters extend into a three-dimensional mapping of the Riemann zeta complex plane, incorporating real, imaginary, and height axes. The Riemann zeta function is a mathematical function whose zeros are theorized to dictate the precise distribution of prime numbers. This graph charts a trajectory within that space. A vector breaks away from the critical line spiral and terminates deep in negative space at the high-state coordinates, -187, -319, and -571. -187 factors into 11 and 17. 11 is the smallest prime associated with elliptic curves lacking complex multiplication. -319 factors into 11 and 29. Their shared factor of 11 creates structural periodicity, generating an exact arithmetic difference of 132. The final negative coordinate, -571, matches the 571-bit length of the NIST B571 standard curve. This is an algorithmic parameter defined by the National Institute of Standards and Technology to secure elliptic curve cryptography. The system interprets these deep negative coordinates as deterministic error vectors. This operates similarly to noise parameters in learning with errors, a cryptographic approach where security relies on finding a specific vector in a high-dimensional lattice. The geometric distance of this vector from the zeta function's critical line calculates mathematical tension, equating lattice distance to cryptographic strength. This graphic displays the value 24257. It serves as the system's central algebraic invariant and primary operational gate. This integer appears in mathematical physics, specifically in denominators of weight 16 motivic multiple zeta values, used to calculate scattering amplitudes in superstring theory. 24,257 breaks down into the prime factors 127 and 191. The system selects these primes for their distinct geometric properties. 127 is the 7th Mersenne prime, taking the form of 2 to the power of 7 minus 1. This anchors the system's logic to binary computer architecture. 191 is a prime that generates a value of -1 within the 24-step modular grid, outputting exactly 24 times 8 minus 1. There is a precise difference between the pure sum of squares, which is 24,097, and 24,257. This difference acts as a phase shift gap that prevents the arithmetic engine from collapsing into a static state. 24, regulating the transition between basic arithmetic and the geometry of string theory. The arithmetic lattice extends into the theory of sporadic groups, specifically the Monster group. This is the largest of the sporadic simple groups, possessing a dimensionality of approximately 8 times 10 to the 53rd. Within the number OS, the integer 196853 operates as a high-energy threshold, categorized as a guardian state. This diagram compares the 196853 invariant against 196883, which is the smallest non-trivial representation dimension of the monster group. The exact difference of 30 constitutes a primordial symmetry break. This gap is the product of the first three primes, 2, 3, and 5. The system utilizes this 30-point symmetry gap to generate the dynamic tension necessary for driving high-state calculations. Crossing the 196853 threshold shifts calculations out of standard linear arithmetic and into the rules of sporadic symmetry. The system decompresses massive numbers using an algorithm similar to a Newton-Raphson iteration. This is a mathematical method used to find successively better approximations for the roots or fixed points of a dynamic function. This graph illustrates a binary cascade. Using the sequence 2 to the power of n times 3, numbers are stripped down through recursive subtraction. 12,288 minus 11,969 locks on to negative 319. 6,144 minus 5,825 also anchors at negative 319. To manage the speed of these cascades, the system integrates Fibonacci damping. A Fibonacci sequence is a mathematical series where each number is the sum of the two preceding ones, acting as a natural mathematical shock absorber. For instance, applying recursive subtraction to 28,757 using the binary step 24,576 yields exactly 4,181, which is the 19th Fibonacci number. This process is defined as mathematical renormalization. It parallels how high-energy physics manages and contains divergent values. This dynamic convergence guarantees stability, filtering the chaotic noise of large primes to isolate the deterministic signal underneath. The central frequency controller for the number OS structure is known as the 12 bridge. Geometrically, the number 12 connects to the foundational constant of zeta regularization, where zeta of -1 equals -1/12. This calculation sets the critical dimension limits required in string theory. This visual maps how the binary cascade leverages the 12 bridge. It takes a smooth, base 3 ternary arithmetic wave and translates it into pure binary power. This structural sequence forces massive composite numbers to yield their internal architecture. Fermat primes are reduced through this mechanism into stable Mersenne primes. The 12 bridge operates as a geometric translator, forcing chaotic prime data to conform to the strict binary rhythms required by computer processors. The theoretical application of the high-state system lies in bypassing the brute force limits of traditional RSA factorization. RSA cryptography relies on the extreme difficulty of locating two unpredictable prime factors hidden inside a massive composite number. This challenge is generally considered NP-hard, meaning there is no known way to solve it quickly as the numbers grow larger. The high-state model claims these composite numbers, known as semi-primes, adhere to a strict 12 and 24 harmonic structural pattern within the zeta lattice. The system evaluates a semi-prime's dissonance against the base 24 grid to identify specific rhythmic stutter points in the number structure. These stutter points correspond exactly to the binary difference between the hidden prime factors. By identifying these specific binary clusters, the system converts them into exact weights for a knapsack matrix calculation. The knapsack problem is an optimization puzzle that asks how to pack items with specific weights to reach a target sum. The total number of possible binary combinations is logarithmically minuscule compared to the massive search space required by traditional prime brute forcing. By identifying binary clusters at these stutter points, the search space for prime factors collapses from a brute force hunt to a targeted search for specific weights in a knapsack matrix. Because these binary combinations are logarithmically limited, the system targets the hidden factors by identifying the rhythmic signature of their difference.